Ahmed.
Okay, thanks a lot, Veronica. Let me begin first by thanking the organizers for the school for inviting me to give this set of lectures. It's really been a lot of fun. And thanks also to all the students for all the really interesting questions. Okay, so this is going to be my last lecture. Before we get into the meat of it, let's quickly recap what we saw last time. So last time we saw how the gravitational fine-grained entropy formula, this formula that came down from above, that it produced sort of an entropy curve for the Hawking radiation as well as the wormhole that's consistent with the central dogma. Right? So this was the formula and was consistent with the central dogma. So that was awesome. So the black hole really does seem to behave like an ordinary quantum system with a finite dimensional Hilbert space. I also discussed how the formula implies this kind of entanglement wedge reconstruction where the inside of the black hole should be thought, or sorry, the wormhole interior can be thought of as part of the radiation, and hence it broke this semi-classical local tensor factor structure on any Cauchy slice. So that spatial locality was broken somehow. And I discussed how this helped evade the firewall paradox, or at least one version of the firewall paradox that I discussed, the one based on the monogamy argument, or this application of strong subadditivity. There are other versions of the firewall paradox, which we didn't talk about, but that goes beyond the kinds of black holes that we're talking about. I also discussed how entanglement wedge reconstruction seems to give a mechanism for information to escape. Here, let's quickly just review that. Here, in these two diagrams here, I'm showing the evolution of a slice of the entanglement wedges for the wormhole. I guess I should write it. This is for the wormhole, as in for the wormhole system as seen from the outside, and also for the radiation. Initially, the entanglement wedge of the wormhole contains an entire Cauchy slice like that, but then it breaks up at some point once you evolve for a little bit of time. While for the radiation, at first, the entropy of the radiation is just given by the entropy of these regions. So this is the entanglement wedge of the radiation. But then after some time, it develops an island. And then the interior of the black hole becomes part of the radiation. The way that this allows information to escape is that if you had a particle in the sort of deep in the wormhole, like this green particle here, at the page time, which is going from this time slice to this time slice, the particle after the page time is no longer part of the entanglement wedge of the wormhole, but is now part of the entanglement wedge of the radiation. But also, if you throw something at a later time, say after the page time here, then, well, the point here is that this initial particle, you had to wait a page time to get it back. But after the page time, any additional particle you throw in, you only need to wait a scrambling time for it to escape the entanglement wedge of the wormhole and appear in the entanglement wedge of the radiation. So that was the recap. Any questions on that? Okay, very good. The final point I wanted to stress about what we discussed last time is this funny aspect here, that this that the von Neumann entropy appearing in the gravitational fine-grained entropy formula has to be evaluated in the semi-classical state. So I didn't explain why. Hopefully it should become clear by the end of this talk. But this is something weird about this formula. You're supposed to, in some sense, you're supposed to assume the wrong answer, but then just fix it up by considering a new formula by adding this area and doing these different procedures. Okay, so today's talk will be about deriving this formula from the gravity path integral. I should emphasize I have not been using this term before as much as I should have. This formula sometimes goes by the name of the island formula for obvious reasons. The idea, the key, is to allow for dynamical gravity when computing the entry. Oops, too big. When computing the entropy of any region of the bath, dynamical gravity. And the method which we're going to use to compute the entropy is just a standard method using the so-called replica trick. Now, the full path integral, or the partition function, if you will, is given by it's an integral over the metric, over the dilaton, with the JT action. That's the model that we're considering, G phi. And also it includes a matter partition function, which I'll just call Z CFT. Oops. On the background, on this hybrid spacetime, which is half determined by G and half is just flat space. So this is the same G here as it is here. Last time we mostly discussed the semi-classicals. Well, the thing I should have emphasized that I'm going to study how this path integral is computed. The thing that we studied last time was the semi-classical saddle of this path integral. By that I mean where you restrict to the Euclidean black hole. Okay, so if you look at this picture here, so in the previous lecture, I was representing the CFT part as a circle, but now I'm drawing it as a rectangle or a square, just for convenience. So what we did was we filled in the gravity region here with just the disk, which was just ADS2, or rather ADS2 on the disk. And so this means that we can approximate, well, on this saddle, the path integral just looks something like this. The JT part just, well, the on-shell, well, this is just the on-shell action of JT on that Euclidean black hole. And then what remains is the quantum part, which is the partition function of the CFT on, again, this hybrid spacetime, but now where we know what the hybrid spacetime is. So let's just write hybrid, where it's half ADS2 and half flat space. We said that this partition function, if you slice it like this, it should give you, it should prepare for you this semi-classical state at this time here, where it describes the eternal black hole in thermal equilibrium with the bath. This should be contrasted with what would happen if we were to consider the full path integral. Okay. In the case of the full path integral, you're supposed to consider all possible gravity configurations within this circle that are consistent with the boundary conditions. Remember, we had these boundary conditions on the metric and the dilaton, and we had Dirichlet conditions. So you're supposed to consider all possible configurations, and they would look something like this. For example, here's the disk. Here's the disk with one handle, the disk with two handles, and so on and so forth. One thing to note is that in the computation of just Z, like literally this thing that we're computing here, this term here dominates. Just the disk diagram or rather just the disk contribution dominates. And one reason to understand why is because of the ground state entropy term. Remember there was a topological piece in JT gravity? For the disk, it went as e to the phi naught divided by 4g Newton. If you add one handle, then the Euler character tells you that this thing should become e to the minus phi naught over 4g Newton, and this is e to the minus 3 phi naught over 4g Newton. So spacetimes of higher topology are more and more suppressed. Okay? So this term here is a leading term when computing this partition function. Any questions so far? Okay. Now, we want to compute the entropy of some region in the bath. So the first step to do that is to define the density matrix of this region. So I'm going to consider again. So I'm going to derive the formula for the simple case of just a single interval on the bath that contains a piece of the ADS boundary. So that's like this piece here, this region Q. The endpoint here is will be labeled by the point B. The density matrix, just formally, is given by this, where you start with the state that's prepared by the path integral, whatever it is. I'm calling it 0, and all you need to do is to get the density matrix of Q is trace out the complement of Q, and this tracing out will ultimately be done for us using the path integral. Let's go through the steps. So so first let's talk about the state 0. So here, this path integral here prepares for you the state 0. It goes from minus infinity up to infinity. Oh, sorry, up to t equals 0. But where in the gravity region, because the thing that I'm trying to do right now is I'm trying to specify sort of the exact state. Okay, I'm not trying to look at the semi-classical state. So the only thing I can specify about the gravity region here are just the boundary conditions. We're going to fill in gravity at a later step. So for now, in the state 0, you prepare some state of the quantum fields on the red regions and some boundary conditions for the gravity and also for the quantum fields on the green region, and then those will be propagated forwards once we consider different gravity configurations. This should be clear, I think, more clear by the next slide. In any case, so this is supposed to be the state 0, well, this is supposed to be, well, this is the state or rather the ket, and this is the bra. Now, to get the density matrix, as I just said, we need to trace over the complement, which means just connect everything else other than Q, other than the region Q, which happens to be here and here. Connect everything else using the gravity path integral. So in the CFD regions, there's just going to be now just identifying the top and bottom pieces. So now it's just, identify those two pieces. And so the path integral just gets, the two regions get glued together. What this picture is supposed to describe is that you're supposed to evaluate the full path integral, both the QFT and the gravity, subject to the boundary conditions on Q, because we are looking at matrix elements, rho I, j. Those are the boundary conditions here, I and j, and also the boundary conditions that we have to impose here, um, which come from specifying the boundary conditions for gravity. So this is supposed to be the full path integral. The key point, the reason why I have not filled in the gravity part yet is because what I mean by all configurations will depend on I and J. In the way that we're going to see on the next slide. Okay, any questions about this? Okay, here's the next slide. So we want to compute the Renyi entropy, which is, let me see actually first. Okay, so we want to compute the Renyi entropy, which is simply the trace of the density matrix raised to the power of Q. Okay? What this means, sorry, raised to the power of N. What this means is you're supposed to consider N copies of the density matrix, as I have shown here. And then matrix multiplication between the different factors of the density matrix are represented by cyclically identifying these copies along the branch, of the branch cut as such. And there's one more that does that. And then the last connection from the last one down all the way to the first one, that's supposed to be the trace. Okay. Now we've sort of finally specified everything about the path integral. So now what this defines for you, what this thing is called, well, this thing sometimes goes by the name of the replicated manifold, which I'm going to call M tilde N. And this thing specifies the boundary, or completely specifies the boundary conditions that you need to consider all the gravity configurations. But the strategy to evaluating this, it's simplified after you do some transformations. The first transformation I'm going to consider is to go to the so-called covering space, where I unwrap this branch cut here. One sort of hallmark of going to the covering space is that the length of the ADS boundary gets multiplied by a factor of n. So if you look at every one of these sheets, the length of this curve here is beta, that's the renormalized length of the circle. And it's the same for every single sheet. But because the boundary Q attaches itself to this circle, this means that this endpoint here gets matched to this endpoint here. And so the circle really is n times the length of the original one. Okay, so now we've sort of massaged the space-time to bring it sort of a nicer form. Now what we need to do is to evaluate or consider the different gravity configurations. So then evaluate gravity, or fill in gravity, let's say. And for the rest of this section, it's going to turn out that the only relevant configuration to consider is the disk. Okay. Some might object and say, but hang on, wasn't the disk the thing that gave you the semi-classical answer at the very beginning that that was quote unquote wrong? Well, this is a different disk, right? This is a disk where the length of the boundary of the disk is n times beta. It's not just beta. Okay, so that's just a comment. So then you would get the spacetime here. And then a trick you can do is you can undo the cover. This is going to be convenient for later purposes, which will hopefully become clear later. So undo the cover. So we unwrapped it, but now we want to wrap it back. What happens when you wrap the spacetime back, or you undo the cover, is that the branch cut, which was originally only in the bath region, extends into the bulk. Okay, so because we filled in gravity here, and now we are wrapping this, and so what can happen is that the branch cut could be somewhere in the bulk. And this spacetime here that I'm drawing here, sometimes sometimes I like to call it sometimes goes by the name of the branched cover, okay, which I will call MN. This MN here should be thought of as the Zn orbifold of MN tilde. I'll sometimes call this the orbifold theory. Okay, let me make some comments and then take questions. So the first comment is that it's an assumption about the kinds of gravitational configurations that we considered when filling in the spacetime here. I'm making the assumption of only considering replica symmetric gravity configurations. Okay? So here there's like a symmetry like this. You divide this pi into n pieces, and the statement is that gravity looks the same in any one of these wedges. This is an assumption, like it's gravity can do whatever it wants. It can break this replica symmetry if it wants. And in fact, this breaking of the replica symmetry is important for certain things, which maybe I'll discuss at the very end of my talk. But in any case, so we want to consider just the replica symmetric ones. It turns out that these are the most relevant for our purposes. The second point, the second and third points are about just the nature of what this manifold looks like, especially around the points B and A. Let's focus on the point B. If we look at the space-time in the replicated manifold, assuming we've sort of filled in these regions here, or equivalently, we can just look here. This is you can see, well, yeah, okay. The point is that on Mn tilde, the angle around B, this point here, is actually 2 pi n. So we have a conical singularity. In the branched cover theory, after we go through this process, we come here. From the branched cover, or rather from the orbifold theory's perspective, you should think of that this point here is actually smooth. The angle is 2 pi, but there's a defect living on it, which which is the twist field. So it's like you're in the orbifold theory, but you have a twist field at the point B. In some sense, like this is kind of semantics, but I think this is the better way to think about it. Now, next, let's talk about the space-time around point A. When we consider gravity configurations that fill in this geometry or fill in this geometry, we are only considering smooth metrics that fill in this the space-time subject to the boundary conditions. And therefore, at any point, even the point A, the space-time should be smooth. The angle should be just 2 pi. However, when we go to the branched cover theory, the angle around A is actually not 2 pi, it's 2 pi over n. Okay, so those were my 3 comments. Please ask me questions about the slide.
I have a question about the orbifold configuration. I'm not sure I understood how it works when you pass from the replicated manifold to the covering space. I understand that, but why when you go back from the covering space to the orbifold, then you just have 1 copy and you don't have many copies with the bulk filled in? I think I don't understand very well how that works. Can you explain one more time?
Let me see. So you can think of this as having n copies, but it's just it's a bunch of sheets on top of one another. And this branch cut, it's the thing that takes you between the different copies, right? Was that your question?
Yes, but so you actually have n copies of that manifold, but they are all, let's say, next to each other, and that branch cut just tells you how to go from one to the other one. Is that the idea? Once you
yes, you can think of it like that.
But then, why don't you have a conical singularity around B? If you still have you have to identify all the copies.
Well, I'm just replacing the notion of saying you have a conical singularity at B by saying you have an operator on B, which is this twist field. That's why I said this might be a semantics thing.
Okay, that makes sense. Thank you.
Yeah.
Can I ask something?
Yes.
I didn't get what your physical motivation was for doing the orbifold and going to this branch cover theory.
Mm-hmm. It will be clear in 2 slides.
Okay, can I just ask, instead of the orbifold, is it possible to just resolve the singularity by just cutting open a neighborhood of the B point and filling in a disk or something like that? That way you don't introduce a singularity at A.
Well, we actually want the singularity at A.
Ah, okay. All right,
Yeah.
thank
you. Any other questions?
Yeah, I was wondering, I'm trying to see the difference between this setup and the usual liquid Malacena, where you, after taking the quotient, I thought the boundary, sort of the bulk, there it sounds like you start with, on the boundary, you have a 2 pi n conical angle, but after taking the quotient, the boundary is smooth. How should I see that difference here?
Well, it's the same thing. So this angle here, so to connect with the in the Lukowitz-Maldacena, well, first comment is that I'm literally following their steps. Second comment is that in the Lukowitz-Maldacena discussion, the space-time ends at the ADS boundary. There's no path, but the equivalent thing would be to take B all the way to infinity. Okay, let's say it like that. And after taking the quotient, and you sort of ignore the branch cut, the length of this circle here is beta, which I believe is what Lukowitz and Maldacena consider, right?
I see. Okay, that clarifies.
Yeah.
Thanks.
Can I ask a question?
Of course.
Why did you, so when you went to the covering space, why do you say that you just have this contribution from the gravity? I mean, you cannot have any higher genus configurations inside the circle?
Yes, you can. But I want to make 2 comments. The first comment is that the higher genus ones they seem to be more suppressed. Remember, by this topological piece that I discussed, you have e to the minus phi naught over g Newton. The second comment is that it turns out that well, we only want to focus, well, it turns out that these higher genus contributions are never saddles. And ultimately, we just want to consider saddle point contributions to the path integral. And those are simply not saddles.
So is that something that will come out of the derivation? Or you assume it and then you justify it later?
I'm not going to justify it in this talk, but there are other works that, show that these higher genus surfaces with one, these higher genus surfaces are simply not saddles. But let me emphasize one thing, that the reason why I only want to focus on saddles is because I'm not powerful enough. There are other models where it is that are simple enough that you can consider the full JT integral over all configurations, arbitrary genus, and so on and so forth. Well, actually, not the entire thing, but at least well, the point that I'm making, the point that I wanted to make was there are models where it's you can sum over. Wait, sorry, let me think. I'm trying to remember if these other models, if they sum over all, if they also include non-saddles, or they simply sum over an infinite number of saddles. I forget what's the statement. Anyways, that's not important. The important point here again is that I'm just not powerful enough to include configurations from all of the gravity path integral. And the simplest thing that I can do is just consider saddles, and higher genus are not saddles. That's basically my position.
Okay, so if I compare this slide with, I think the last to last one, this one. So the diagram that you have in the bottom, you are not considering the second and the third diagram. Yeah. Okay.
Correct. I am not considering these because they are not saddles, and I'm not powerful enough to compute them.
Thank you.
Mm-hmm.
I have a question.
Yes.
So this is sort of in context to the connection between random matrix theory and JT gravity. So to the extent that I understand it, it's only after you do disorder averaging that you get I guess sort of a smooth geometry. So that when you're looking at the saddle points of the JT path integral, are you sort of just thinking of it as just like the disorder average version of some random matrix theory? You're not actually looking directly at, I guess, these microstates?
Yeah, this point that you're mentioning is a question of interpretation, and I guess okay, two comments. Yeah, well, in the way that I'm setting up the problem and the calculation, I'm kind of assuming that this is not it's not dual to some average. It's dual to a definite. I'm working with a definite system, and I'm just computing the entropy of some region. The other comment, which is perhaps I think what the disorder average people would say, is that the quantities that I'm considering, like the Renyi entropy and the entropy and so on, these are quantities that self-average. So so here it's a trace of this density matrix. It's a trace of many different terms. And so all the randomness just gets canceled out. And so the results that I'm telling you today, even though you might say, but hang on, JT gravity is dual to a random matrix where you average. These results should also carry through to theories that are not where you don't disorder average, simply because these are self-averaging. This is a self-averaging quantity, the trace rho to the n. I hope that addressed the question.
Yeah, but I also have a follow-up question.
Yeah.
So this idea of self-averaging, I mean, if you just look at, I guess, the spectral form factor, I think after the scrambling time, self-averaging kind of breaks down. So if we're looking at this in sort of the black hole context, if you were to throw a particle into the black hole and you wait a scrambling time, you can sort of say that from the perspective of an outside observer, the particle hasn't actually fallen into the black hole. It's like almost like a Planck unit away from the horizon after a scrambling time. So
sorry, go on.
So if you're to ask questions for very, very long times, is that like saying that this picture doesn't work anymore if you're asking questions for very long times?
Correct, but I don't think I'm looking at questions at those kinds of questions. And I'm not sure that scrambling time is all you need. And also, I think this question is a bit too far afield. Maybe we should save it until either the end of this talk or during the question answer period with Douglas, who's I think more qualified to answer.
All right, thank you.
Yeah. Okay, so let me move on. So the upshot of the slide is that you ended up with this branch point in branch point A inside the bulk. Let's say a few more things about A. If you when you restrict to the disk and you assume replica symmetry, basically the only parameter, the integral over the dilaton in the metric becomes an integral over A. So A parameterizes gravity configurations. I'll just say gravity configurations. Okay, so different values of A correspond to different configurations of gravity. And ultimately, what I'm going to do is that, so I'm going to have an integral that looks something like this. I'm integrating over A. And I will focus on saddle point contributions and ignore non-saddles. So just ignore these guys. And so basically A will be fixed by equations of motion. Okay, that's what I'm going to do. So I'm just priming you from now. Okay, let's see. The next thing I wanted to say is how to extract the entropy from the action. So the thing that we've been discussing so far is writing trace row to the end as there's this path integral on replicated manifold or replicated geometry or whatever. And implicitly, there was a normalization, which I didn't talk about. There's a normalization, which you'd need to get the fact that trace row is equal to 1. So if I take n goes to 1, I should get just 1 again. Z1 here is just it's the very first example that we considered, just a path integral with just 1 copy. Having trace row to the end, you extract the von Neumann entropy by just taking the derivative with respect to n and taking n goes to 1. And you can convince yourself that this is equal to this quantity here. So it's the derivative of log of Zn divided by n. Okay. This is something I'll let you do offline. But let's consider this quantity. This quantity is here. So on any gravitational saddle, this log Zn breaks up into 2 terms. The first term is just minus 1 over n times the JT action, evaluated on the replicated geometry and tilde, plus the logarithm of the CFT path integral also on the replicated geometry. That's replicated manifold. So that's this picture here. But it would be more convenient for us to express everything in terms of the orbifold theory, where we assume replica symmetry. The reason is the following. So when you go to the orbifold theory, you simply have you have n copies of the action. So this 1 over n term here disappears. Okay, so it does not appear in this JT term. However, notice that this configuration in the orbifold theory, I should write this down. This orbifold theory, it has a singularity, this conical singularity at A. But there's nothing in this JT action that would generate such a singularity. And so you would need to add this new term, which is sometimes called the cosmic brane term. So you need to add cosmic branes, which source this conical singularity. At A. The point, so that's the thing there. Sometimes A is minus A and minus A is A, but don't worry too much about that. The point is that here there's no singularity, but after you do the orbifold, it looks like there is a singularity. And so it must be that the theory, so the JT theory here had no cosmic brane term, but the JT theory here must be fixed, must be modified to add this cosmic brane term to be consistent. Okay, and so that's what the gravity part does. And the matter action, what it does is, from the orbifold theory's perspective, it simply looks like you are computing a twist field correlation function. Okay, that's where one of the twist fields is at minus A and the other one is at B. And they are the things, the object, they create a branch cut which allows you to go from one sheet to the other sheet and so on. Remember, this is the orbifold theory. It's n copies mod Zn. Any questions about the slide?
Yeah, so is it obvious why the conical singularity is at minus A? Could it be somewhere else, like sort of the fixed point of the Zn symmetry?
Good. Actually, that's a thank you for reminding me to stress this point, that the point minus A is the fixed point of the Zn symmetry. So minus A so far, I didn't tell you where it is. I just claimed that it's somewhere in the bulk. I'm going to go back up the slide. And the location of A, it parameterizes the different gravity configurations. Therefore, we're going to integrate over A. Then the equations of motion are going to fix for us the location of A. Was that your question?
Yeah, but I guess then my question becomes, how do you know the twist sort of this branch cut extends all the way to A, not to somewhere else?
By somewhere else, you mean somewhere else in the bulk, or somewhere else like you mean somewhere else like here, or do you mean somewhere else like here?
Or say in the bulk, it just that we sort of said it just extends to the bulk, but didn't say where it extends to.
Yeah, well, A is not fixed, right? So I don't know what A is, but it's going to be determined.
We're defining A by the fixed point of the Zn symmetry. So, but then there's sort of a different concept of where the twist, sort of the branch cut, ends at. Is it obviously the same?
I think so. I think just by definition of saying that it's the fixed point of the replica symmetry means that that's where the branch cut has to end.
I see.
Yeah.
But that's what's the argument for that?
Because, well, if I do this, well, if I go around this, that's a manifestation of the replica symmetry.
I I see what you mean.
Like the only fixed point is this point. Oops, this is the fixed point.
I see. Okay. Okay. Thanks.
Any other questions?
Yes. So in your last line, like you have like a 2-point function between two twist fields. And how do I see like where does the cosmic brain contribution carries over from the second to last line to the very last line?
Here to here?
Yeah.
So good. So the cosmic brain comes about when looking at the gravity solution. If you look at the gravity solution here, this is secretly just a it's just a giant disk of length n beta, and it's just shaded in, just ADS2 on a disk, and it's smooth. There's nothing fancy about it. But then when you go to the orbifold theory, you quotient this by the Zn symmetry, and then you get a picture which looks like, use a different color for the cut, like that. If you look at this picture, well, this space-time, it looks like you have a conical, you have a conical singularity here. So it must be that the JT theory here in the replicated, well, the replicated JT theory must be equivalent to a orbifold JT theory plus cosmic brain. Because otherwise, you don't have anything to generate for you this singularity in the bulk. I'm just saying by consistency of going between these two pictures. Does that make sense?
Yeah, it does. Thank you.
Yeah. Okay, so let me move on. Okay, the reason why I wanted to work on this orbifold theory or this branch cover theory is that n becomes just a parameter. It doesn't have to be an integer or anything. It's basically just tells you the strength of the conical singularities that you have in the orbifold theory. And I want to study the theory at two values of n, one where n is equal to 1, and one where n is almost 1, where it's near 1 from above. If n is equal to 1, we're just back sort of at square one. We have the original semi-classical saddle, where the gravitational where that saddle is simply the Euclidean black hole at some temperature beta. Okay. With this configuration, the JT action plus the cosmic brain term just becomes a JT action on just M1, which was just one copy of the disk. The point, well, that's what the gravity does, and the matter action. What happens to it is that the twist fields disappear. The point is that when you go all the way down to n equals 1, there's no more A and B. There are no conical singularities. Okay, so that's just sort of a sanity check. If you now consider n near 1, the way you should think about this is that it's a deformation of the n equal to 1 solution. Now, if you deform this action away from the n equals 1 solution, so here it is again, the first order deviation will just be proportional to the equations of motion times the deformation of the metric. And since we're interested in saddles, this thing is just going to be 0. The other deformation, well, the other correction, or the other term of the interesting thing that happens is that the cosmic brain term comes back when n is near 1. This thing just goes to this, it's not equal. The coefficient is not 0 anymore. 1 minus n is small, but it's not 0. And something similar happens to the matter term. For the matter term, you end up with this twist field correlation function. Well, first the twists are back, so let me emphasize that. And the nice thing is that they're back, but they're also on the n equals 1 semi-classical saddle. Which means that this quantity here is nothing but the von Neumann entropy of the interval that goes from minus a to b. Not only that, but it's also the semi-classical entropy, because we are on this manifold M1, and the path integral will just automatically produce for us the semi-classical state. And so this is the entropy in the semi-classical state. Okay, that's one upshot. The other upshot is that the only terms that depend on n are this, oh, it's too small, are this term and this term as well. Which will be important on the next slide. Any questions about this slide?
Should that n be 1 over n? I think in your earlier slide you had 1 over n.
Yeah, sorry, I did have 1 over n. So why did I put 1 minus n here? Oh, no, this is not, this is right, because I'm doing this. 1, so here I have 1 minus 1 over n. But this thing is just n minus 1 divided by n. But n is near 1. So this thing is approximately 1 minus n. Well, n minus 1.
Yeah, I
Does that
see.
make sense?
Yeah.
Okay. Any other questions? Okay, we have everything we need. So let's put everything together. So, well, essentially what we found is that near n equals 1, the trace row to the n looks something like this. It's an integral over dA, or integral over a, the different gravity configurations, where the action gets replaced by this quantity here, which is nothing but the generalized entropy. This is S gen from minus A to B. And we want to consider just saddle point contributions to this integral. Well, then it's again e to the S gen evaluated at the different saddles, assuming there are many saddles. And so extremality, so what we see is that extremality comes from the saddle point condition, that these are saddles. So that's the fact that varying with respect to A of Sgen is equal to 0. And minimality comes from the competing saddles. And so this tells us that the entropy is given by this. Any questions? Okay, excellent. So next, I wanted to talk about another example. a more interesting example. This is going to be very quick. Just going to draw pictures. Let's imagine doing the same thing for computing the entropy of the Hawking radiation. Now, by the Hawking radiation, I mean a region that looks something like this. Okay, this is what we discussed last time. Again, you have to follow the same procedure, consider many copies as such. And then you have two different ways, or it turns out that in this case, there are two different gravity saddles that are relevant. One where the one which you can call the semi-classical saddle. Or the Hawking saddle. Where the gravity part of each copy of rho to the n gets separately filled in. And so when you collapse it down to the orbifold theory, you just get this. And there turns out to be another configuration where the different gravity regions of the different copies. So here, this is the case for n equals 3. Okay? The gravity regions of the different copies get connected by a wormhole, and which in the branched cover theory, or the orbifold theory, looks something like this. So the emergence of this wormhole is represented by the emergence of these new branch points and branch cuts. With the locations, now you have two locations, A1 and A2, that's like this point here and this point here on the other side. And again, these A1 and A2 parameterize for you the different gravity configurations. And you have to integrate, well, you have to find the values of A1, A2 that satisfy the gravity equations of motion. So in this case, the interesting thing in this case is that there are two saddles and they compete. So it's this thing plus, well, versus, let's say, and one dominates over the other, depending on the amount of time in Lorentzian time that you evolve the system in. Any questions?
So it looks like these have different Euler characteristics. So the reason that one dominates at late times, it's overcoming the exponential suppression.
Yeah, so good. Essentially what happens, so we can just write it down. So if you look at trace rho to the n, for this term, it's going to be e to the minus maybe 1 over 1 minus n or n minus 1, I forget. Minus 1, phi naught plus phi at A1 divided by 4g Newton, plus the same thing for A2, plus the von Neumann entropy of the matter, the two regions, plus e to the minus n minus 1 of just this von Neumann entropy of these regions. The point is that, so as you noted, initially, like this thing has this extra suppression factor. There are two factors of phi naught over 4g Newton, or e to the, so this goes e to the minus n minus 1 times 2 times phi naught over 4g Newton. But the point is that this term decreases as a function of time because of because this entropy here continues to increase as a function of Lorentzian time. The entanglement between the Hawking radiation and the interior of the wormhole continues to grow using from that line we were drawing before. But this answer here is just constant, but it's a very large constant. but nevertheless, it's a constant. And so then this term eventually beats it. As in the exponent here eventually becomes larger than this exponent. Did that address the question?
Yes. So I'm wondering now, the higher topology in the covering space, is there a similar story there? Will those eventually dominate as well?
The higher topology, you mean like the wormholes that look like that, or like?
So I'm thinking on the picture that's drawn for n equals 3. If you add a handle there, will it eventually dominate in the same way?
So those have the first immediate comment is that those have not been considered. The other comment is that it's a property of JT gravity that I don't think you expect that such wormholes are saddles. The configurations with handles here are not saddles. That's one comment. Another comment, which I guess maybe I should have said before. Well, because they are not saddles, so nothing supports, like there's no nothing fixes their size. Okay, so I'm drawing a wormhole here. You have to integrate over all possible sizes of this throat, and so you have to contend with studying the path integral of a quantum field theory on a wormhole that can become arbitrarily small, arbitrarily thin, and that actually gives you a divergence. So the nice thing about these kinds of wormholes is that they are saddle points and they're macroscopic. They're large, and they don't have such a divergence. Should have emphasized that this thing here is called the island saddle, or sometimes wormhole. Saddle. Yeah, anyways, I hope that addressed the question.
Yes, thank you.
Any other questions? Okay, the last example is probably the easiest one, which maybe I should have started with, is the entropy of the entire bath, including both ADS boundaries. So from one perspective, this is the total entropy of the union, or the entropy of the union of the wormhole and the Hawking radiation. So we're considering the entropy of this region, union this region. Clearly in the semi-classical description, this thing is not the entire system. There's all of this part. But gravity does not cease to amaze. So consider again the same computation. So what you have to do is you have to consider the density matrix and take n copies. Note that so we have not filled in gravity yet. Note that this entire half region here gets glued to the entire top region here. But the gluing, the gluing is only along the blue lines. Okay, this means that you can rearrange this this product, or this trace row to the n. You can rearrange it to give you something like this, where you take this bottom half and you connect it to this top half, and then separately this bottom half with the top half of the one after it, and so on and so forth. And so then you get basically this picture factorizes into a product of n path integrals, which look like this, with a circle of length beta. Okay, these are now separate calculations. Well, the nice thing is that each one of these guys is nothing but trace row. And so what we've shown is that trace row to the n is equal to trace row all to the power of n, but trace row is just equal to 1. So this is equal to 1. So trace row to the n is equal to 1. So now if you take the derivative of trace rho to the n with respect to n, with respect to n, well, that's taking the derivative of 1, which is 0. So you find that gravity tells you that the entropy of this region is actually 0. And so gravity amazingly anticipates holography. As I like to say, gravity knew about holography before Huang. Okay, and so gravity tells us that you should replace this by, oops, with this. We have R, BR, L, BL. You should think of the system as being dual to some quantum mechanical system composed of something at this boundary coupled to this path, and similarly on the other side. Any questions about that?
Yeah, so I had a question about the n copies that you have of just like a single boundary. Could you not, in principle, have have contributions of wormholes connecting all of those, like, and those would spoil your argument for getting one?
Good, excellent question. I can give you, I'll give you two answers, one of which is a cop-out, and the other one which is, I guess, more serious. The cop-out answer is that you don't expect these wormholes to be saddles. Okay, so and so there's a question of whether you should include them or not, and so on. But the better answer is that trace rho to the n is actually equal to, better way, well, the actual quantity that we're calculating is trace rho to the n divided by trace rho to the n, something like that. Like, this is the normalized trace rho to the n. And what this calculation is telling you is that this quantity here is equal to trace rho all to the n, and so this is literally equal to 1. This is independent of how you choose to evaluate this side of the equation. There could be wormholes connecting this to itself and this to its bottom and the bottom to itself and so on and so forth, but just like everything has to conspire to give you 1 at the very end. I hope that was clear.
Okay, good. So basically you have to be careful with the normalization of your path integral. Okay.
Yes.
Thanks.
Ahmed, you have 5 minutes.
Okay. The last 5 minutes, I just wanted to make some extremely schematic arguments about entanglement wedge reconstruction and how acting on the radiation can affect the interior. But again, it's going to be extremely schematic and it's just going to be very cartoony. I should refer you to the paper of Pennington et al. Sorry, it's 1N. That has a much more lengthy discussion on this and much more sharp. So let's suppose I give you 2 orthogonal states, 0 and 1, each of which has the following semi-classical description. So 0 has a description where you have a particle 0 here that falls in. It's a particle in some state 0, and is orthogonal to this particle here that falls in some state 1. Okay. The thing that I want, okay, so these two guys are orthogonal. So from the semi-classical bulk description, it looks like the particles are deep inside the ADS region. The question is now whether one can find, well, to demonstrate this non-locality, is whether you can find an operator purely on the bath, okay, not even on the ADS boundary, that can transition between O tilde and 1 tilde. Right? That it can take you from 0 tilde to 1 tilde. So basically, the question is whether this expectation value can be non-zero. Clearly, if it's space-like separated from them, from a semi-classical perspective, it should not be successful in doing this. That this transition amplitude semi-classically should be 0. Okay, so this quantity here, the expectation value of OB, can be written as such, where because O is only supported on some region B of the bath, then you can, then this expectation value is a trace of OB times trace of B bar of this ket bra 01. Okay, this is just simple algebraic manipulation. Now, the key point is to choose O, to choose a special O that will get the job done for you. And the O that you have to choose is this thing. It's an operator which acts on B. So this region here is the region B on the bath. It's a combination of both. It's a combination of the bath on both sides, and it's cleverly designed to give you. Oops. Cleverly designed that it has its own ADS spacetime with a particle 1 and a particle 0. Okay, I'm free to do that. Now this trace here, you can just you can given this description, you can conclude that it should look something like this. It looks very similar to O. So so this part here is a complement of B bar. Well, not quite, not just that. It's also everything here as well. So you've traced out everything here using the full path integral. But the thing that we learned from the previous discussion is that even when you have the path integral of gravity, you should not be too hasty in filling in the space-time. And what you end up with is the following. So we're trying to compute this quantity. This quantity, the matrix, the contraction between O and this trace B bar looks something like it's these contractions of these red lines. So, so it doesn't matter which is which. So let's say this is O and this is the state. So the matrix contractions contracts this guy to this guy, and this guy to this guy, and similarly here to that, and here to that. And now you can consider to fully compute this quantity, you need to consider all possible gravity configurations that contribute. One configuration is quote unquote semi-classical configuration, where the gravity part in OB and the gravity part in this density matrix, well, it's not really a density matrix, but this quantity here, the gravity parts separately fill. So that's like this thing here and this thing there. Well, clearly, if these guys fill in by themselves, well, the contraction between this particle 0 and this particle 1 will give you 0. Because as we declared, these are orthogonal states. But if you allow for connections between the operator and the state, like this thing here, a wormhole connecting like that, then you can get a contraction between the 1 of the operator to the 1 of the state, and the 0 of the operator to the 0 of the state. So this thing in general is not equal to 0. So it indeed can offer a transition between these two states, even if this operator is acting far away in the Bath region. I like how Douglas Stanford describes this phenomenon. He says that it's your operator somehow simulates the black hole or the ADS spacetime, and it generates a wormhole from that simulated spacetime to the physical one, which allows for such a transition and access to something which is naively very far away. Okay, let me end on that note. Thanks a lot.
Thanks very much for wonderful lectures. Okay, so we have, I guess, a little bit less than half an hour before the official Q&A, but let's take a few questions now and then stop the recording and continue in the Q&A.
Right. I have a question. If this is too big and you'd rather ask and answer in the Q&A, let me know. But in here, where in this step was it essential that we were working with an ADS boundary and in 2D? Why did we need those approximations? Were just to make the calculation easier, or is there some physics here that would be different if we were trying to do asymptotically flat or in higher dimensions?
Okay. The reason again is, I mentioned this before, it's the fact that we want a way, well, okay, so first, if you ask me if I believe that everything I said applies to flat space or not, I would say yes, it applies to asymptotically flat space. However, there are some technical, let's just call them technical difficulties, which is that so in all of my calculations, I always specify a region of the bath, and then I try to evaluate the full path integral, or at least I look at saddle points of the full path integral. Something which was convenient in this discussion is that I am able to that when there's no gravity in this region here, considering different configurations of the gravity path integral does not change what I mean by the interval. Gravity changes things here, but not here. And if you are in asymptotically flat space, and this is now it's a gravitating region, but in asymptotically flat space, then in principle, you should allow in your path integral for configurations that modify this region as well, also would get modified. Maybe there's a clever way of evaluating the gravity path integral in asymptotically flat space that can tell you that actually these configurations that change the asymptotic region are actually highly suppressed and they're not important and so on. But I don't have a quick argument for that. But I expect that would be what should happen.
Yeah, that makes a lot of sense. Thank you.
Yeah.
And for higher dimensions, do you have a similar conceptual hurdle, or is it just a computational one?
It's computational because computing entanglement entropy is difficult.
Okay, fair enough. Thank you.
Yeah.
Stefano?
I have two quick questions. One quick question and one not so quick. So if you want, I can delay that to the Q&A. The quick one is just if you can comment about, do we know how complex these operators that you're talking about must be in order to build these simulated spacetimes? And does that depend on what kind of state you have in the bulk and so on? The other one, I'll just throw it out, but if you prefer, I can ask it later. is, okay, so in this situation, we're always asking like a CFT question in flat space-time. So we are taking an interval of the path and we are asking a question about the entanglement entropy of that. And asking that, it comes kind of natural to use the replica trick, like you always do in QFT, CFT, and then just fill up whatever is in the middle. And so you get these replica wormholes. But if you don't have such a like ordinary, let's say, QFT question, is it natural in some sense to consider replica wormholes? What I mean is like, could have we guessed that there were replica wormhole saddles if we weren't asking a question that naturally leads to the replica trick? And so if those saddles are actually relevant for other situations or not, and so on.
Yeah, let's start with the second one. Yes, replica wormhole-like configurations were considered previously. The first thing that comes to my mind right now is the semi-classical ramp, which you heard about, I think, yesterday or the day before. So it comes up when you're computing quantities that involve multiple copies of the system. And like in the spectral form factor, you're computing z squared or zz star, and then you can have a wormhole connecting these two. So that's an example where you had a wormhole, but well, I don't know if do you want to call that a replica wormhole? I mean, yeah, why not? I mean, you've replicated the system, and so you have a wormhole. Yeah, did that answer your second question?
In part, yes, but it seems
Okay.
like this you actually want to compute the entropy between, in some sense, two systems. So in replicated systems, you have two systems. But in this case, you just have one system and you want to compute entanglement entropy of a region of that system or some other quantity. So I just don't understand how natural can it be to consider multiple systems, replica wormholes, and the limit and goes to one as a part of that solution if you are not calculating something that is naturally calculated with a replica tree.
Yeah, good. I see your question now. Yeah, it's yeah, I don't have a direct answer, but it's just one can wonder, is the replica trick a necessary thing for computing entropy? And in some sense, yes, because the entropy is not something you can measure. It's not the expectation value of a Hermitian operator. It's a thing that you can compute, or well, at least you'd have to do a very intensive quantum tomography, or quantum state tomography, which involves having multiple copies of the system and so on. So the entropy is intrinsically a multiple copy thing, and so wormholes, like, it seems to me like they had to show up, these replica wormholes. I mean, there are other quantities, not entropy, but like, for example, this thing about this entanglement wedge reconstruction. It's kind of a there's a souped up version which is discussed in this paper of Pennington et al., where again they consider an operator is the Peitz map, which again involves multiple copies, and I think it's kind of the same idea in spirit. You need to know details of the state in order to be able to apply the right operator, which can affect the interior of the wormhole. But in order to know what the state is, you need multiple copies and so on. Like it's kind of the same spirit. You also asked about the complexity of this thing and how long it takes to to implement. I forget what the quantum information is of this thing, but maybe you can ask Douglas. All I can say, I'm pretty sure that's an extremely complicated thing, which would take is it exponential in the entropy, maybe? Maybe an exponential time in the entropy to implement? That would be my guess, but I'm not sure.
Thank you very much.
Shreya?
Yeah, I think in one of the early slides, you had a picture where I think you were justifying why we calculate the Renyi entropies of this state, which is prepared with the Euclidean path integral, although what we're eventually interested in is the time evolved state in this evaporation process. And I was just wondering if you could explain that part again.
Was it this slide?
So I think it was one of those, like the slide before this or the one before that.
I think it was this slide. So,
okay.
So the point, let me see. So correct me if I'm wrong. It's trying to answer this question: why do we consider the semi-classical entropy? Is that the question?
Shreya, your microphone somehow went off locally.
Oh, sorry. Can you hear me now?
Yes.
Oh, okay. Yeah, sorry. So I think that, no, sorry. So the state that we're working with in this whole process is the one which is prepared with this Euclidean path integral associated with some temperature beta. And I was just trying to understand sort of where that, like how the information about the time evolution is contained in that.
Oh, good. Good. Something I did not emphasize is that you should think of my path integrals are like Schwinger-Keldysh path integrals. So there's a contour that there's a Euclidean part, and there's a Lorentzian excursion, if you will. So like, you know, I've been drawing pictures that look like this, right? You should think of there being like, you go up to here and then you go like that. You take both the path and the ADS boundary to some in some Lorentzian direction. So this direction here is like tau, and then this direction is like IT. Although I was not very explicit about this, but the path integral really it has a Euclidean part, and then it also extends into the Lorentzian part. In fact, that's important. In this story here, it turns out that in simplest cases, there is no saddle for if you take the diagram I have here literally, where both B1, A1, A2, and B2 are all have zero Lorentzian evolution. But once you analytically continue these times to Lorentzian time, which is like saying that your path integral now has an excursion in Lorentzian time, then comes back down to zero again. Only then do you find a saddle point. That's a statement that, if you remember, we had the island the island contribution started at some point only. That's that statement. That only once you evolve in Lorentzian time sufficiently do you start getting is this thing a sort of honest to God saddle point.
I see. Okay, thank you.
Yeah.
Let's see who was next. I guess Aritra.
Yeah. So can you hear me?
Yes.
Yes.
Okay. So I'm still having difficulty in trying to understand why at the very beginning why your point A ended up being inside the gravity region. So can I think of it in terms of if I forget about this orbifold and everything, and in the very first lecture you mentioned that the ADS2 has a boundary which is allowed to freely wiggle inside the bulk region. Does this have anything to do with that? In other words, can I say that in order to capture the gravitational part of this path integrals, it is necessary for the point A to actually go inside the bulk?
I feel like, well, we're trying to go from.
So maybe I should phrase it in a different way. You also mentioned that the point where A ends up is fixed by the equation of motion, but naively, if I think that A is a boundary point, it shouldn't contribute to the equation of motion, but it does. So can you explain why?
No, I'm just going to try to explain why A is somewhere in the bulk.
Okay.
So I think we should all be okay with this picture here.
Yes. Yeah.
So we have a disk which is whose length is n times beta, and should I say this? Then I'm going to take an orbifold where this circle here gets cut down by a factor of n. I feel like the only way you can do this, well, I feel like in any way you can do this, you would always generate some branch point inside this region here. Like there was because this circle here is not a fixed point of this Zn quotient that I'm about to do. The quotient has to be somewhere inside. Sorry, not that, the fixed point, sorry, has to be somewhere inside. I feel like there has to be a theorem like that.
Okay, yeah, I understand that part. But then I think, so, I mean, is it necessary to go to the orbifold picture? I mean, is it possible to work everything out in the covering space and then keep A at the boundary?
So if you work only here, then yeah, so I agree that there won't be any branch point, and in principle you can work in that theory, and you should get all the right answers. But it's a lot more convenient to work. The reason why it was convenient to work in a branch cover, maybe this is your question. The convenient it's this aspect here. Is that you can then write down the action of the replicated manifold as just n times the action of the branch cover theory, plus this cosmic brane term.
Okay, so yeah, so I see. So yeah, if your A is on the boundary, then I think the cosmic brane term wouldn't be present in your.
Exactly, but also, yeah. but A cannot be on the boundary, right? Because we said that the circle here goes from n beta to beta.
Yeah, well, when I said A on the boundary, I meant if you stay in the covering space picture and not before.
I see. Yeah. Then you'll just have a harder time maybe evaluating this action. Like that would be my only guess.
Okay,
but in principle, maybe this is something you should try. Like start with the equations in this picture and then transform everything back and just see what you get.
Mm-hmm. Another question I had regarding this this semi-classical picture that, so I mean in all this calculation we have been doing everything semi-classical except the wormhole contributions, right? So that's something that we wouldn't expect naively if we were to look at this whole problem from a semi-classical perspective, if we don't consider the path integrals.
Mm-hmm.
So
yes, go on.
Right. I mean, I was just making a comment that You were making this comment yesterday, I think, that we do some semi-classical calculation, but we end up getting something which is a very, quantum gravitational, if I use that word, such as, having different entanglement wedges talking to each other. And those things reflects in the fact that you have wormholes here.
Exactly.
Right. So apart from, I mean, one could say that we are doing a semi-classical calculation, but then these wormholes actually capture that extra bit that gives you the quantum gravity effects.
Yes, but it's surprising that it's a quantum gravity effect that you can state somewhat semi-classically, like you can like you don't change the pictures by much. Like well, sorry, it's just a comment that you continue to assume the semi-classical quantum state of the matter, but you just modify the formula for computing the entropy. That's all I'm emphasizing.
Okay.
Yeah.
Okay, I see. Thank you.
So I propose, I know there's still 2 more hands up, but we have only some 7 more minutes before the Q&A. So unless you have a really burning question you want to ask now, I would propose postponing your questions to the Q&A so that we can all take a little break. And so is that okay? Great. So let's thank Ahmed again